In this video, we'll look at a little bit more the details of why it's difficult to train deep neural networks. So I mentioned in the previous video that historically we've often found that training a single hidden layer neural network without, say, a second hidden layer, like in this case, would often work better than having two or more hidden layers. And even though there are some problems where we'd actually think that we would gain by having many hidden layers. So what I'll talk about in this video is two types of reasons where we tend to see this difficulty, which will help us then introduce ways of addressing these difficulties and solve our problems and get effective learning algorithms or deep neural networks. There are actually two types of problems which are or difficulties which are quite different. So the first is that training a deep neural network is a harder optimization problem than training a single hidden layer neural network. In particular, so in this case, we would be in an underfitting situation where if we had a better optimization procedure, then we should be able to, if indeed we're having a harder time to optimize our neural network, then it means we probably could fit the data better. So it would be then an underfitting situation, which would mean that we would get better results in generalization by optimizing better and fitting better our training data. So this difficulty of optimization is often illustrated by the vanishing gradient problem, which is a well-known problem in neural networks. It essentially corresponds to the following situation. So if we go back to the backpropagation algorithm, we know that whenever we're taking the gradient of the activation of a unit and then we passing that gradient to get the gradient of the pre-activation, we have to multiply by the partial derivative of the activation with respect to the pre-activation. Now, if the hidden unit is at its or close to a saturation point, that is, it has its activation close to the highest or lowest value it can take, it means that the partial derivative is going to be very close to zero, which means that the gradient with respect to the pre-activation is going to be close to zero because we're multiplying by that partial derivative. And so it means that at this point now all the gradients being backpropagated towards the other layers below is going to be very close to zero. And if we repeat this process many times and we have many saturated hidden units, it means that as we get closer and closer to the input layer, we get gradients that are closer and closer to zero. So that's why we say that the gradient is vanishing. And this is essentially caused by the saturated units. Because saturated units has essentially a partial derivative of zero, and so that essentially shrinks the gradient towards zero. And so that's a big problem because intuitively the advantage of having hidden units that are nonlinear and saturate is that it makes the prediction nonlinear, and we want that nonlinearity. So we actually want the neural network to get to a regime which is close to the saturation point to take advantage of the nonlinearity of the hidden units. But as we get there, we get gradients that become closer and closer to zero, and you get towards a vanishing gradient situation. And so there's sort of this dilemma here, which is very unfortunate, which is that when we get to a situation where we're starting to be in an interesting configuration of the neural network, which is nonlinear, well, it becomes actually harder and harder to optimize because the gradient becomes very small for the first hidden layers, which might not train at all with respect to how quickly the top hidden layers would train. And which means that these hidden units here, these units here might start to adapt to hidden units that are more or less random because they're not actually training as quickly as the connections that are here, for instance. This is in fact a well-known problem in recurrent neural networks, the fact that there's this dilemma between getting gradient that passes well through the hidden layers and being in a situation where the neural network is in a configuration that allows for saturation and is more interesting. I'm not going to talk about this too much, but there's quite a few papers about that. So that's the first hypothesis, that optimization is harder, and this is made harder in particular by the fact that hidden units saturate and block gradients when we backpropagate them towards all the lower hidden layers. A second possibility is that we are actually not in an underfitting situation, but in an overfitting situation. That is, when we're considering the possibility of having many hidden layers, it means that we're exploring a more complex space of functions. So functions are more and more complicated, and there are many, many more of them that are functions as we add layers, and possible functions we can model. And also, just one way of sort of informally measuring the complexity of a space of functions is to consider the number of parameters if these functions are parameterized. So in the deep neural net, the parameters are all the connections. And of course, when we add more layers, we have more parameters. So we can expect that perhaps we'd get some overfitting problems where we'd be in this high variance, low bias situation where the family of deep networks corresponds to a very large space of possible functions, and for a given training set, there'd be many functions that would reach, say, zero error or close to zero error. And also, if we varied the training set, because our space of functions is very, very complex and can adapt very easily, then we actually get very many different neural networks as we, say, vary the training set. So this would correspond to high variance. We have low bias because neural nets have a lot of capacity. Deep neural nets have perhaps even more capacity. So for any training set, it's actually able to reach a very low training error because of that high capacity. And so we might be in a situation where the variance is too high, and even though we have low bias, and thus we're not great at generalization, and thus we're overfitting. So these two problems are actually quite different, but depending on the situation, the intuition is that there's one that dominates over the other. So if we are underfitting, and there are ways we can try to measure this, if the training error is very close to the validation set error, then perhaps we're underfitting. Then one solution is to use better optimization methods than just stochastic gradient descent. And this is a current active area of research, as in right now, 2013. And I'm not going to talk too much about this because I don't want to talk too much about optimization in this class, but there are references on the website of this course. We're going to talk more about the second hypothesis, overfitting, which in my experience tends to be more prevalent in problems where, say, we're doing classification, for instance, which is the main topic of this class. And now the approach is essentially going to be to use better regularization methods for deep neural networks. And we'll look at two types of regularization approaches, one which is based on the incorporation of unsupervised learning in the training procedure, and another one which is based on the use of so-called dropout training, which is also which we can understand as a way of improving regularization in deep neural networks.